We turn now to the thermodynamic potentials from which all the equilibrium properties of a system can be derived, and in particular the definition of these thermodynamic potentials in terms of partition functions. We see that there are different potentials for different circumstances: constant entropy, constant temperature, constant pressure. So now let's move to a rather general discussion of types of thermodynamic potential. In Appendix D, or E rather, we derive the Clausius inequality. This is shown here. It says that the change in entropy minus the change in internal energy of the system plus the external pressure times the change in volume, all divided by temperature, must be greater than or equal to 0 in any process. The derivation of this comes from taking a large system, the world, coupled to the system of interest, and realizing that in the total system the change of entropy must be greater than or equal to 0. So from this potential, let's just take a look at some limits now. If we are not in contact with a heat bath, so it's a genuinely isolated system, which means that the internal energy cannot change and the volume is a constant, then in those circumstances, in the Clausius inequality, the only relevant thermodynamic parameter is the entropy, and the statement then is that for an isolated system, the change in entropy is greater than or equal to 0. So, to find the thermal equilibrium of an isolated system, we maximize the entropy. Now, in the event that we are in a system in contact with a heat bath at constant volume, in this case delta V is 0, and so multiplying this equation by T, we arrive at T delta S minus delta E is greater than or equal to 0, or alternately, E minus Ts, which we will call a Helmholtz free energy F, must be minimized. So for a system at constant temperature, we minimize the Helmholtz free energy. Finally, for a system in which all these variables can change, we call this free energy the Gibbs free energy, and this is minimized for any thermodynamic process. So we choose a thermodynamic potential then according to whether the system is isolated, maximum entropy, in contact with a heat bath only, Helmholtz free energy, and we minimize the Helmholtz free energy in any process, or in a system in which the volume can change as well, the Gibbs free energy, and we minimize that. So now let's take a look at how we would obtain the appropriate thermodynamic potential from the partition function. We saw earlier that we can write the entropy as the Boltzmann constant times the log of the partition function plus the thermally averaged energy divided by temperature for a system in contact with a heat bath. And so you will recognize, if you compare this with the definition of the Helmholtz free energy, that the Helmholtz free energy is given by minus Boltzmann constant times temperature times the logarithm of the partition function. So here you see how a thermodynamic potential is derived directly from the partition function. So if you can count the number of microscopic states of a system, you can calculate the Helmholtz free energy and thereby all of the equilibrium thermodynamic properties of a system. The Gibbs distribution becomes even more useful when we generalize it to include the idea that particles might be able to enter and leave a system. So this is the previous definition of the Gibbs free energy. And then we add to it a term mu called the chemical potential times the number of particles in a system. This will be a very useful result when we consider, for example, chemical reactions where the number of particles changes, equilibria between different phases where the number of particles, for example, in the solid phase versus the gas phase can change, and a result we'll use when we do quantum mechanics. For the chemists amongst you, this quantity here, E plus PV, is what's measured by calorimetry and is called the enthalpy H. So let's take a look at the definition of the Gibbs free energy in terms of a partition function. To generalize to the case where the particle number can change, we need to generalize the Boltzmann distribution to the Gibbs distribution. And here it is. It says that the probability of having n particles in state R is given by a Boltzmann factor, and beta here is equal to K1 over Kt. So beta times mu n minus E nr, and we then have to normalize that by summing that factor over all states. And this z now is called the grand partition function. That sum is written out on the slide. And by analogy with the derivation we showed earlier for the Helmholtz free energy, the Gibbs free energy is given in terms of the grand partition function by minus K Boltzmann times temperature times simply the log of the grand partition function. We'll use that result later. I want to end with a note about nanoscale systems. Macroscopic systems are characterized by the fact that the thermodynamic quantities are all extensive. Double the size, one doubles the energy of the system. In a nanosystem, the size of the system plays a key role because in a nanosystem, in addition to the interaction energy represented by this mu that you may have between particles in the bulk of the system, you have a different interaction energy between particles on the surface of the system because they now no longer have partners surrounding them. This means that the absolute size of a system plays a role in nanothermodynamics that is not the case for extensive variables in genuine thermodynamics or macroscopic thermodynamics. This system of thermodynamics has been worked out by including something called a subdivision potential, shown here on this slide in a generalization of the Gibbs free energy. However, we are going to cheat and simply add terms proportional to surface area when we deal with the thermodynamics of nanoscale systems.